When you turn on a standard light bulb, it emits thermal radiation. The light is messy, scattering in every random direction and color. But a laser operates on an entirely different set of rules, producing an intense, tightly focused beam of coherent light. To understand exactly how that level of control is achieved, we are going to look back at a physical principle discovered in 1917, and then use it to conceptually assemble a working laser system from the ground up. Building one requires three essential components. Think of them as items on a workbench: an energy source, a gain medium, and an optical resonator. By combining these three basic elements, we can harness quantum physics to directly manipulate how light behaves in space and time. Our physics engine begins with Albert Einstein. In 1917, he realized that to maintain thermal equilibrium, there must be a third undiscovered way light and matter interacted. Here, an energy ladder illustrates these interactions. Top, absorption moves an electron up a rung. Middle, spontaneous emission drops it randomly, releasing scattered light. Panning down shows stimulated emission. A passing photon strikes an upper rung electron, forcing it to drop and emit a second photon. That newly emitted photon is an exact physical clone of the first one. It travels with the exact same phase and in the exact same direction. One photon goes in, two identical photons come out. This quantum cloning process is the actual optical amplification that puts the A in the acronym laser. To make amplification self-sustaining, we prepare the gain medium. We force atoms into population inversion, pushing more atoms on the upper rung than the bottom. If we fail, atoms stay at the bottom, absorbing passing photons and instantly killing the cloning chain reaction. This schematic details how systems achieve inversion. While a two-level system fails, stages 3 through 6 show a functioning three-level laser. By utilizing a metastable intermediate state where electrons can accumulate, a population inversion is successfully established, making optical amplification possible. Depending on the design, this gain medium can take several physical forms. It could be a solid-state crystal, a glass tube filled with gas, or a flowing liquid dye that allows you to tune the specific wavelength. The gain medium you select dictates exactly how efficiently your laser can be forced into that state of continuous optical amplification. Now we apply the first component on our workbench, the energy source. To drive those atoms into the excited state, we apply a pump source. This is usually an intense optical flash lamp, or a high-voltage electrical discharge firing directly through the medium. As the pump injects energy, the system approaches a tipping point known as the lasing threshold. This is the exact moment where the rate of optical gain finally overtakes the system's internal losses, like light scattering off impurities. This chart plots that exact tipping point. Below the threshold, the medium just produces a slow, dim glow, but the instant the threshold marker is crossed, the cloning reaction takes over, resulting in a vertical spike of exponential amplification. By adjusting how we supply that power, we control the output. A steady pump yields a continuous wave, while pulsing the energy releases the light in massive, concentrated bursts. Once that lasing threshold is crossed, the device stops being a simple glowing tube and officially operates as an optical amplifier. Now, the optical resonator. Here, we trap the gain medium between two mirrors. One is 100% reflective, the other, an output coupler, reflects roughly 98%. Trapped light bounces back and forth, gaining cloned photons, until the intense beam escapes through that partial mirror. Setting this up requires strict physical alignment. First, verify the power is off. Next, use precision micrometers to adjust the mirror mounts. Finally, put on safety goggles before initiating the test sequence. Engineers typically use slightly curved mirrors rather than perfectly flat ones. The curvature keeps the bouncing light converging toward the center, preventing it from wandering off and escaping the sides of the cavity. The geometry of this cavity dictates the final cross-sectional shape of the beam, which we call transverse modes. This image displays several variations. Engineers usually calibrate the resonator to isolate the top left pattern, the perfect solid circular spot of the fundamental TEM00 mode. The optical resonator acts as the steering wheel. It takes chaotic quantum amplification happening inside the medium and enforces discipline, forging an engineered tool. With the alignment complete, we can execute the sequence. The power activates the pump. The medium reaches population inversion, and stimulated emission triggers a massive photon cascade. That raw cascade bounces through the optical resonator, filtering the noise until a brilliant, highly stable beam shoots out of the output coupler. Looking at this active helium-neon system, you can see the glowing discharge and the resulting beam. Whether you are operating a massive industrial crystal laser or a microscopic semiconductor diode in a barcode scanner, this foundational sequence of components remains exactly the same. By combining an energy source, a gain medium, and an optical resonator, we have successfully manipulated the quantum states of matter. We gathered random thermal energy, aligned it, and forged it into the most precise form of light in the universe.